Welcome to my channel. If you like my videos, then kindly subscribe, like and watch. Thank you.
Welcome back. In this lecture, we will discuss the method of superposition. So, before starting, let me describe what is method of superposition. So, method of superposition can be defined as the net response caused by two or more stimuli is the sum of responses that would have been caused by each stimulus individually. So, you can see that there are two stimulus, that is concentrated load and uniformly distributed load. So the effect of these two stimulus will be equal to sum of the effect of this stimuli or this stimuli. Clear? Or we can also define as the method of superposition is that the load effect that is caused by two or more loading. So you can see there are two or more loading. So in this case there are two loading and their effect or the cause effect by due to these two loading will be equal to sum of load effect caused by this loading 1 and the sum of effect of this load 2, that is W. Clear? Their effect sum will be equal to the total effect of these two loading. So this is method of superposition. Clear? So we can see that deformation of this is a beam that is one end of the beam is pin supported at point A, while at point B there is a roller support and two different loading concentrated load of 150 kilonewton is acting at point D and uniformly distributed load of 20 kilonewton per meter is acted on this beam. Clear? So we due to this loading we will have certain deflection and slope. Clear? So we can also find them by the method of superposition, that is we will split this beam into two type of loading, that is loading 1 and loading 2. Clear? So in loading 1 we will only represent the concentrated load while the rest beam and supports are same, and then we will also have a second type of loading that is only uniformly distributed loads. Clear? And the rest of the beams and supports will be the same. Now we will find the slope for this loading 1 and deflection of for loading 1 and slope for loading 1 as well. Clear? This is loading 1. Clear? And we will also find the deflection for loading 2 and slope for loading 2. Now the sum of effect of loading 1 and loading 2 will be equal to total deflection of this loading, that will be equal to y1 plus y2. Clear? And similarly the slope will be also slope due to loading 1 plus slope due to loading 2. Clear? So principle of superposition is deformation of beam subjected to combination of loading may be obtained as the linear combination of deformation from individual loading. So this deformation of this beam can be obtained by the linear deformation of individual loading, and then at the end we will add them in order to find the net deformation or slope. So procedure is facilitated by the table of solution for more common type of loading and problem. So basically in this type of problem we will use the table that is available at the end of book as appendix 4. So there are certain templates are available, and we will quickly use that templates instead of solving this problem that will go long. So we will simply use that table. I will show you this table. This is the book of mechanics of material by Baer and Johnston, and this is 7th edition. So if you go at the end of the book, that is appendix, and in appendix if you go to beam deflection and slope, so these are the tables that is available. You can see The table includes different column. This is beam and loading. This is elastic curve. Column 3 is maximum deflection, slope at end, and equation of elastic curve. So if you have this type of loading, so elastic curve will be like this, the maximum deflection will be this one, the slope at the end will be this one, and an equation of elastic curve is this one. So you do not need to solve or calculate these are this. You can easily use this table and in order to to find the slope at the end, equation of elastic curve, and maximum deflection. So we will use these tables and we will take out the deflection and slope at the end or at any point. So we will use them in our problems. Clear? Okay. So let's move further. We will solve a simple problem in order to have further clarification or clear picture of how method of superposition works. So you can see sample problem 9.7. There is a cantilever beam that is fixed support at point A. Now from point C to B there is a uniformly distributed load. The total length of the beam is L. Clear? And the uniformly distributed load is acting only on the half length of the cantilever beam. So for the beam and loading shown, determine the slope and deflection at point B. So you have been asked to find the deflection at point B. Clear? And slope at point B. Now if you look at this figure is not available in this table. Clear? Let me show you the whole table. So this figure is not available in this table. So what we will do, we will use the method of superposition in order to convert the beam into this. Clear? So what we will do is that I will add a uniformly distributed load over here so that it may become same like available in the table. So I have added this uniformly distributed load between A and C. So in order to remove the effect, I will also add some load below so they may cancel each other. So now we can see that we have this loading. So we have this loading, and due to method of superposition we have converted this load into a loading type 1, that is whole of the beam is acted upon by a load W. Clear? And the second one is this downward loading, not downward but the load that is acting below the beam. So this is the loading 2. Clear? Now these two sums will again give you the same beam. So what we will do, we will solve this loading 1 in order to find the deflection at point B and slope at point B. Similarly, we will solve loading 2 in order to find deflection at point B and slope at point B. Now from this you can see that this deflection at point B is YB and slope is theta B. Now here this is for loading 1. So this will be YB1. Clear? Let me zoom it so that you can easily see. So this is YB for loading 1 and theta B for loading 1. Similarly, this is YB for loading 2 and theta B for loading 2. Sorry, this is loading 2. Clear? Okay, so let's move further in order to solve this. So we will take this loading 1 that is shown over here, and then for loading 2. So now you look at this loading 1. This loading 1 is similar. This picture is similar to this loading. Clear? So you can see that the column 3 is maximum deflection clear, and the slope at the end. So this is similar to this one, clear. So we need the slope at point B, which is this one at the free end, clear. So maximum deflection or deflection at point B for loading 1 will be same this, which is minus WL4 over 8 EI, and slope at the end, which is at point B, slope at point B is for loading 1 is again this value, which is minus WL cube over 6 EI. So you can easily take this value in order to find the deflection and slope. So you note this value, clear. These are the same value that is written over here. So for loading 1, slope at slope will be equal to minus WL cube over 6 EI, and deflection is equal to minus WL4 over 8 EI. Now for loading 2, it is given, this is the slope and deflection diagram. So you can see these are for loading 1, clear. Now for loading 2, you can see this is the loading 2, and it is only acting on half of the beam, and you can see that at point C there will be a deflection due to loading 2 and slope at loading due to loading 2. But at point B there will be also slope and deflection. So we will tackle it in a while. So let's start with the loading 2. So for loading 2 here there is something tricky, not tricky, but you can easily tackle with them. So if instead of whole beam, so you can consider the loading till here, clear. Let's move toward the toward these equations again. Now you can see, if I draw my beam, so the beam was like that, the loading is now upward, and this is the fixed support, clear. So this is W, and this length is L by 2, clear. Rest here the load is downward and here the load is upward, so only the effect will sign will be positive, but it is for length L and here it is for length L by 2. So YB for loading 2 will be equal to it will be plus sign, and if instead of L you will put L by 2, clear. So you will get the value I will write in a while. Similarly, theta B for loading 2 will be the same. This will be plus sign and L will be replaced by L by 2, clear. So their values are I will write their values. This loading of loading due to this loading at point, okay, so remember that this loading is not at point B. Here you can see we are going to take the point C, clear, point C. So this loading will be YC, clear. Similarly, this theta will be YC, and when you put L is equal to L by 2, so YC will be equal to WL cube WL4 over 128 E into I, because L will be replaced by L by 2, so when you solve it, it will be WL4 over 128 EI. Similarly, the slope at point C will be equal to WL cube over 48 EI, clear, and it will be plus because the force is upward, so the slope and deflection will be also upward. So now you can see that due to loading 2, the slope at point C is this one, and deflection at point C is this one. So this deflection is, if I zoom it, so you can see this is the slope at point C due to loading 2, and this is the deflection at point C due to loading 2. Now if this slope is a straight line in segment CB, there is no loading, so the bending moment is 0 and elastic curve is a straight line. So it is a straight line, so it means the slope at point C is equal to slope at point B, which is equal to same WL cube over 48 EI, because slope at point C is this one, this one, this one. Clear? So they both are same. Now the slope at point B is this one. This is the total slope. Clear? And this is equal to slope at point C plus this perpendicular distance. Clear? So how we will find this perpendicular distance? So you can see there is a triangle. I will draw a triangle. Clear? And this is theta C2. So you will take tangent of theta C due to loading 2 is equal to perpendicular over base. Clear? As this theta is very small, so tangent of theta is equal to theta C due to loading 2 is equal to perpendicular over base. So perpendicular will be equal to base into theta C due to loading 2. Now you can see this base is L by 2, which is mentioned over here. So L by 2, B is L by 2 and theta C is WL cube over 48 EI. So now YB, total YB, deflection at point B is equal to YC2, which is equal to this one. We have already find out deflection at point C due to loading 2, and this perpendicular distance, which is equal to B into theta C due to loading 2. So B is L by 2 and theta C is 4 WL cube or 48 EI. So when you sum it, you will get the deflection at point B due to loading 2, which is 7 WL4 over 384 EI. Clear? Now you have total, you have deflection at point B due to loading 1, and you have deflection at point B due to loading 2. Similarly, you have slope at point B due to loading 1 and slope at point B due to loading 2. So you can add them to find out the total deflection at point B and total slope. So you can see, combine these two solutions. So if you add total deflection at point B is equal to total deflection at of point B due to loading 1, clear, and due to loading 2. So when you add this is negative and this is positive. So when you add them, so you will get total equation of total deflection at point, slope, not deflection, theta is slope. So you will have the equation of slope for equation of slope at point B. Similarly, the deflection at point B is equal to deflection at point B due to loading 1, this one, clear, and deflection at point B due to loading 2, which is this. So you have this value and this value, you can also add them, so you will get this deflection at point B. So this is method of superposition in order to find the slope and deflection. So the net effect of this loading is same as the sum of effect of loading 1 and loading 2. I hope it is clear to you now. Now moving further, we will discuss the application of superposition to statically indeterminate beam. So we will also apply the knowledge of superposition on indeterminate beams in order to find the unknown reaction forces. You can see this is a statically indeterminate beam. This is a beam with the fixed support at point A, and there is a rolling support at point B, which is replaced by reaction force, and that is acted upon by uniformly distributed load W. Clear? So method of superposition may be applied to determine the reaction support reaction at the support of statically indeterminate beam. So you can see at fixed support we have three unknown reaction AY, AX, clear, and MA, clear, and there is a reaction support due to rolling. So there are total 4 unknowns, and we have 3 equation of equilibrium. So it is statically indeterminate. So what we will do is that we will divide this loading into loading 1 and loading 2. How we will divide it? Loading 1, and this is loading 2. Clear? So what we will do is that you can see you have a uniformly distributed load, and there is a reaction force. So if we consider one of the reaction force is redundant reaction. Redundant reactions are those reactions that due to this reaction the beam is indeterminate. If we remove these redundant forces, so the beam will be like this, and you can see now there will be 3 unknown reactions, and we have 3 equilibrium conditions, so you can solve this type of problems easily. Clear? So what we will do is designate one of the reaction as redundant and eliminate or modify the support. So here we have removed this reaction as redundant reaction and modified our problem like this. So determine the beam deformation without redundant support. So you have to determine the deflection and slope for this. Clear? Similarly, you will also use the same. Now what we will do, we will treat W as redundant. So when we remove W as a redundant, so there will be a reaction force. Clear? So now we will also solve this type of loading and find the deflection and slope. And at the end, this is for loading 2. This is for loading 1. Clear? At the end, we will get the total deflection is equal to, total slope is equal to slope due to loading 1 and slope due to loading 2. And total deflection is equal to deflection due to loading 1 plus deflection due to loading 2. Clear? So let's move forward and solve a problem in order to show you how we will solve how we will use method of superposition for solving statically indeterminate beam. So sample problem 9.8. So you can see this is a beam that is acted upon by uniformly distributed load as shown. So there is a roller support at point A, roller support at point B, and a pin support at C. So the distance between the roller supports are 2L by 3, and from roller support from point B to C it is L by 3. So total length is L. The question is that for the uniform beam and loading shown, determine the reaction at each support and the slope at the end. So you have to find the reaction force at A, at B, at C, and slope at point A. Clear? So you have to find the reaction at each support and slope at point A. Clear? So if you draw the free body diagram of this this beam, so you can see that these are the 2 support, and if roller support is replaced by reaction support, so it will be like this. Now from our this table you can see that there is a beam under uniformly distributed load W, and there is no reaction force. So you can see that there are one reaction force, 2, 3, clear, and a uniformly distributed load. So if we treat this load as redundant, clear, and remove it, so it will be loading 1, clear. And similarly, if in case 2, if we treat this W as redundant and only represent this reaction force, so our beam will be like this, and this is loading 2. Now you can see this figure is same as the figure that is available in this appendix, clear. So we can have slope, this is the deflection y, this is slope, and this is the equation, elastic curve equation. Let me show it as well. So this is the maximum deflection, the column 4 is slope at end, and the column 5 is equation of elastic curve, clear. Okay, so release the redundant support at B and find the deformation. So we will release the redundant force and we will find the deformation. Apply a reaction at B as unknown load to force 0 displacement at point B. Now you can see that at point B, clear, it's the total deflection is equal to 0 because there is support, roller support, and at any support, rolling support or pin supports, we have studied that deflection will be equal to 0, but we have split it into loading 1 and loading 2, so you will have to find the deflection at point B, which is YB1 due to loading W, clear, and then you will have to find the deflection at point B due to this reaction force RB, clear. Now this YB W plus this YB due to reaction force, their sum must be equal to 0 because at point B there is a rolling support. So when you will have this value and this value, when you add them, so you will get a unknown reaction force, which is RB over here. So let's move forward. You can see that we will take the first loading 1, that is you can see this is the same as represented over here. Okay, so if you look at this loading 1, so this is 2L over 3 and L by 3, and we have been asked to find the deflection at point B. While this loading, the deflection is maximum deflection at the middle. So we are not interested in the deflection at the middle point, so we cannot use this deflection as well as slope equation, clear. So what we will do is that we have equation of elastic curve, so we will use this equation in order to find the deflection at any point X. So if you look at, we are interested at point B, and point B is at a distance X is equal to 2L over 3. So if we put X is equal to 2L over 3 in this equation, clear. So this is also mentioned over here. So instead of X, we have taken 2L over 3, clear. So when you solve it, you will get deflection at point B due to loading W is equal to this value, clear. Okay, now loading 2, which is this one. So if again you look at the table, so we have the loading that is available here, that is case number 5. We cannot apply the case number 4 because the load is concentrated load is acting at the middle. So our case is similar to case number 5, but here the loading is downward, and in our case our loading is upward, RA is upward. So it's okay, we will use the negative sign as positive, because for here the downward force, the all the values are uh, negative. Clear? So we will use the sign convention in order to get our desired result. Okay, so redundant reaction at loading is equal to this one. So you can see that due to this loading at this point, clear, at this point, clear. Okay, for x is greater than or equal to a. So you can see in table we have two values, for x is less than a and for x is equal to a. So in our case the loading is same at here. A is 2L over 3. Let me check. 2L over 3, and this is A and this is B. Clear? Let me write over here. This is A and this is B. So x is equal to A. So A is 2L over 3. Clear? So we will use this equation of elastic curve. So we will use this equation of elastic curve and we will replace A and B here, because here it is A and B. So in our case A is 2L over 3 and B is equal to L over 3. So if you put A and B value, so you can see A is this one, this was A. So in our case it is 2 3 over into L and B is L by 3. So if you solve it, so you will get the deflection at point B. Clear? So this is the value. Now for compatibility with origin, we have said that at point B total deflection is equal to 0. Clear? So this YB is equal to 0 and that is equal to deflection due to loading W plus deflection due to loading R. Deflection due to loading W is this one. Clear? That is mentioned. And deflection due to reaction forces is this one, and this is this one. So when you add them or when you solve this equation, so you will get the reaction force at point B. Clear? Now you have reaction force at point B. Clear? You have reaction force at point B. Clear? So we can use the equilibrium method further in order to find the reaction support at RA and RC. This is very easy. You can solve it by yourself. Clear? So you will get RA and RC. You will simply use the static or method of equilibrium to find RA and RC. Clear? Now we will move further in order to find the slope at point A, because it is given that you have to find the slope at point A. Similarly, slope at point A is equal to, this is loading 1 and this is loading 2. Clear? So we will go to appendix of this table. So you can see this is the slope. Clear? So here you can see the slope will be the value is plus minus WL cube over 24 EI. So that is negative, because you can see this slope is at this point the slope is downward. Clear? So it is clockwise, sorry, the slope is downward and this theta is clockwise from this original because it is downward. Clear? So this theta is negative and this is the same, minus WL cube over 24 EI. So you have taken minus WL cube over 24 EI. Clear? Okay. So 1 over 24 is actually this one. So this is theta A, slope at point A due to loading W or loading 1. Now slope at point A due to loading 2 or reaction due to loading R. So we will move toward that table, that is this table. So you can see we have two equations, one is this and one is this. So at point A and at point B. So if you are finding at point A, so you will use this equation, and if you are interested at point B, so you will use this equation. So at point A we will use this equation, clear, but this is negative because the load is downward. So in our case the load is upward, so this theta will be positive. So we will use this equation, and also we will use the value of B over here, clear. So when you use this equation and put the value of B, that is L by 3, and you will solve it, so slope at point A due to loading R will be this one. Now net deflection at point A is deflection this plus this, that is mentioned over here, you can see, clear. So this is this value, and theta A due to loading R is this value. So when you add them, you will get the slope at point A, which is equal to minus 0.00769 WL cube over EI. So this is how we can solve the indeterminate beam by using the method of superposition. Again, I will summarize it. In this indeterminate beam, we have to find the reaction forces and slope at point A. So first we have what we did is that we applied method of superposition. We split the load into loading 1 and loading 2. How we did it? We consider the R as redundant, and we express the beam like that. In second case, we consider W as redundant and represent it over here. Now we find out the deflection and slope for loading 1. Similarly, deflection and loading for deflection and slope for loading 2, clear. Then we use the method of superposition when at point B it is given that at point B it was given that there is a reaction roller support. So at point B the deflection is equal to 0. So these two, the deflection due to loading 1 plus deflection due to loading 2, their sum must be equals to 0. So from that we get the reaction force at point B, clear. Once you have this reaction, you can also use method of equilibrium in order to find the other reaction forces, and the same method is applied for slope. So the slope at point A is equal to slope at point A due to loading 1 plus slope at point A due to loading 2, and we sum that and we get the total slope at point A due to this loading, combined loading. I hope you have enjoyed the lecture. If you like my video, kindly subscribe, like and watch. Thank you.